My name is Chaitanya, Physics faculty at Shakthi International School. In this video, we are going to learn about an important topic of class 12th from first chapter, electric charges and fields. We are going to learn about equilibrium of charges. Equilibrium of two charges or equilibrium of charges. Okay. So in this case, to understand the equilibrium condition and all, we have to learn a little bit about, we have to know a little bit about force. Whenever two charged particles are there, let's say Q1 and Q2 are two charges which are separated by a distance r, the electrostatic force between them is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. This is a data we already know. So combining those two, electrostatic force can be written as Q1 Q2 divided by r square. If we are removing this proportionality symbol, we have to introduce a constant. Then the constant that we are introducing is what we are calling it as Coulomb's law. Okay, Coulomb's constant. This is your Coulomb's law. Okay, we have seen Coulomb's law, and according to Coulomb's law, this is the data of forces, how they will be proportional. This is called Coulomb's constant. Coulomb's constant. Okay. Now, further, when we are trying to understand the value of k will be written as 1 by 4 pi epsilon, where epsilon is the permittivity of medium. Permittivity of medium. Okay. So now, if the two charges are kept in air or vacuum, okay, then you can represent that permittivity of free space or vacuum as free space or vacuum. This is the symbol we call it. This is called permittivity of free space. Permittivity of free space or vacuum. Okay, and we know there are certain values. What is the value of epsilon naught? 8.85 into 10 power minus 12 Coulomb square per Newton meter square. This is the value. And if you are talking about Coulomb's constant k, it can be written as 9 into 10 power 9 Newton meter square per Coulomb square. These are the values of epsilon naught and k. Okay. So now, what do we do knowing about these values? Why do we have to use it? Whenever there are two charges, okay, both the charges exert forces on each other, we are learning. Okay, this, let's say if it is positive charge, this is also positive charge, the forces on them will be in opposing each other. You can write this one as force F12 and this one, the force acting on it, as F21. F12 means force on one due to 2. F21 means force on 2, charge 2 due to charge 1. Okay, now the distance between them, you should know that force F12 will be equal to F21, because in both the cases when you are substituting the charges, you are substituting k, q and q2 divided by r square only. Okay, the directions are different. If you are writing in a vector form, F12 is equal to minus of F21. Okay, so now whenever two charges are there, this is how their forces are acting on it. Let's say if you are having multiple charges, if you are having q1, q2 and q3, let's say there are three charges now, each individual charge exerts a force on other two charges. If I am asking you to find F net on charge 3, then electrostatic force always acts along the line joining the centers. You can draw this force, okay, this force as F31, and you can write the force acting on 3 due to 2 is F32. So we are having two different forces, there is an angle between them. When you have two different forces, there is an angle between them, you can find the resultant force. Now that resultant force will be given by adding these two forces vectorially, F32 and F31. If there are n number of charges, then the resultant force will become F31 plus F32 plus F34 plus F35 plus up to so on F3n. Okay, vector addition we have to do. This is called principle of superposition. Principle of superposition. Why we are learning about this, sir? Now, to understand the equilibrium of charges, okay, of any two charged particles or any particular system of charges. Let's say Q1 is one charge here, Q2 is one charge here. These two are separated by a distance between them as R. Now, the questions that will be asked will be in this format, where you will keep the third charge such a way that it will be in equilibrium position. Where will be the equilibrium position of the charge, third charge that you are about to keep? Now, it depends on what is the nature of these charges. Let's say this is a positive charge and this is also a positive charge. So you can find three different regions you have. This is the first region, this is the second region, and this is the third region we have. In three regions, we can keep any other charged particle, but we have to find a position in such a way that the charged particle, if you are keeping it at that location, the force acting on that particular charge should be 0. Then only we can say it is in equilibrium. Okay, that means equilibrium specifies, equilibrium means F net being 0. So now let us assume, let's say if I am keeping one small positive test charge Q naught. Q naught is a small positive test charge. Okay, if I am keeping it in the location 1, okay, if it is kept in the location 1, the forces acting on it will be, let's say I am taking this one as charge 3, this one as 1 and this one as 2. It will be experiencing a force in this direction F31, and it also experiences a force in this direction F32, since both are positive charges. So the net force in this region will never become 0. So this is not the region where I can keep the charged particles. So where else I can keep? Can I keep it at region 3? No, that is also not possible. So only region that I can keep is at 2, region 2. So I can keep, let's say if a Q naught charge is kept here, due to this Q1, F31 will be acting in this direction. In this direction, F32 will be acting. If F32 is equal to F31, precisely the magnitude I am talking about, then charge 3 will be in equilibrium. Okay, so now given knowing this one, we can write F31 is equal to F32. What is F31? How we can write F31? F31 is equal to F32. You can write K Q naught Q1 divided by distance between them. Now we have to take the distance between them, right? Since the distance between these two charges, if I am taking it as R, and if the condition is given that Q1 is smaller than Q2, let's say I am taking the distance from here to here as X to that particular charge. The remaining distance from here to here will be taken as R minus X, I guess. Yes, I hope you are understanding it. Now, the total distance between them is R. From that concept only we are writing this. Okay, so we are having Q1 and Q0. These two are kept at a distance of X. If you are writing F31, you can write KQ1 divided by X square, Q0 Q1 divided by X square, which should be equal to F32 when you are finding these two charges. This is Q0 charge and this is Q2 charge. These two are now kept at a distance of R minus X. So now when you are writing K Q0 Q2 divided by R minus X whole square. So now from this condition, if K Q0 is getting cancelled, Q1 by X square can be written as Q2 divided by R minus X whole square. So now this is an important equation. You can solve this equation further giving you different details. Okay. So we can solve it like r minus x divided by x whole square can be written as q2 divided by q1. So r by x minus 1, okay, can be written as under root q2 divided by root q1 when we are sending that square this side. So you can write r minus 1, okay, divided by x is equal to root q2 divided by root q1. Further, r by x can be written as root q2 plus root q1 divided by root q1 when we are taking LCM of it. So further, if you are writing x, you can write it as root of q1 divided by root q2 plus root q1 into 1 by r. This is how we can write. Okay, sorry, not 1 by r, multiplied by r. Okay, this is how we can write the equation of it. Root q1, we are just cross multiplying it, this one, all the terms are coming here. So this is the value of x. So that means x should be root of q1 divided by root q1 plus root q2 into r. This is the distance at which you have to keep that charge so that it will be in equilibrium. Okay, so the same can be changed. They can be asking a different question, different format. Okay, in that they might give you both unequal charges, okay, both of opposite magnitude. Let's say this can be positive, this can be negative. The magnitude of q2 is greater than magnitude of q1 if I am giving, then you cannot keep a charge very close to q2 since it is already greater. You are going to keep it in this region. The q0 will be kept in this region so that the forces acting on it, let's say this is a third charge, since this is positive, F31 will be acting in this direction. Since this is positive, negative charge will attract it. F32 will be acting in this direction. Substituting both, F31 should be equal to modulus of F31 should be equal to modulus of F32. So because magnitude only matters, we are talking. So distance between these two is r, and the distance from this charge to this charge is going to be r plus x, given considering the distance from these two charges x. So if you are doing the same problem again, you will be getting q1 divided by x square will be equal to q2 divided by r plus x whole square. The change is only in this. Initially it is r minus x, now it is r plus x. So you can write this one as q1 by q2 is equal to x square divided by r plus x whole square. So from this equation, root q1 by root q2 by root q2 is equal to x by r plus x. So if you are taking it as an LCM, okay, root q2 divided by root q1 is equal to r plus x divided by x, which can be written as r by x plus 1. That will be further written as root q2 minus root q1 divided by root q1 is equal to r by x. Further, if you are writing it as x, you can write it as r into under root of q1 divided by root of q2 minus root q1. This will be the final formula that you will be getting. So I hope you understood the equilibrium of these charges and where the object should be, or the charged object should be kept, okay, in order so that it will experience net force due to other two charges is 0. You have to go accordingly with these formulas. Okay, we'll see an example problem. Let's say we are having two charges, 9q and 16q. Okay, if I am giving this is negative and this is positive, obviously in this condition I have given the distance between them, let's say the distance between them is, let's say, 2 meters. We have to find what is the x value. Okay, so now if you are trying to find the value of x, since these two are opposite charges, you have to keep it at this location, okay, so that f net can become 0. So this will be r and x, all of that we know. R is 2 meters into under root of q1. Okay, this will be q1 according to our condition and this is q2 according to our condition. In this formula we use this because q2 is greater than q1, magnitude of q2 is greater than q1. Substituting that in this condition, you can be writing it as 2, which is r. I hope you can see it now. R, I am substituting in place of r as 2 into root of q1. Q1 is 9. Okay, so 9 will be written as 3. Under root 9 can be written as 3 root q divided by under root q2 can be written as 4 root q minus root 3q. So now these two gets all the root cubes get cancelled. You can write as 2 into 3 divided by 4 minus 3. So this will be 6 meters. So you are going to keep that charged particle at 6-meter distance, so that your F net on that particular charge will be 0. The equilibrium position is at 6 meters. That's how we calculate. I hope you understood this equilibrium concept well. We'll meet you in the next video. Thank you.